next unit is on transistors. Transistors, as we will see during our discussion, that it has major two applications. The first one is as an amplifier. And the second major use for transistors is as an electronic switch. As a switch, basically a transistor is used in digital electronics. So, basically we will be concerned with the use of transistors as an amplifier, and of course, we will specify the conditions under which it can act as a switch as well, but we will not go in details of switching behavior of transistors. Now, transistors are of two types. One is NPN transistor and the other is the PNP transistor. These are the two types, and you will know, and as you must be knowing, that diode was a two terminal device, and two terminal device cannot act as an amplifier. There should be at least three terminals. In fact, there are three terminals in transistors, and the input signal is given which is amplified. Amplification we may consider a voltage amplification or current amplification, but it will be good enough if we talk mostly in terms of a voltage amplification. Now, let us see first these two transistors, NPN and PNP. A NPN transistor can be shown, for example, like this. This is the three dimensional figure for a transistor, where we are talking of NPN. So, this is N type semiconductor, this is P type semiconductor, and again N type semiconductor. There are ohmic contacts. By ohmic contacts we mean that because the contacts are of two types, ohmic contacts and rectifying contacts. Ohmic contacts are the one in which if we change the direction of the battery, then the behavior remains the same, unchanged behavior for changed polarity, that is ohmic contacts. So, these are ohmic contacts, one here, and the other here on this surface. This is called emitter, this is collector, this is base. So, E, remember E stands for emitter, B for base, and C for collector. But instead of drawing these three dimensional figures to make life simpler, we normally will draw two dimensional figure. So, for a NPN transistor, this will be this. These are ohmic contacts, this is N, P, N, this is collector, this is emitter and this is base. And in PNP transistor the structure will be like this. PNP, P type emitter, N type base and P type collector. And again here these are the ohmic contacts, this is emitter, this is collector and this is base. The circuit symbol for NPN transistor is this. This is E, that is emitter, collector and base. And as we will see later that this direction of arrow, this is actually the direction of emitter current in the transistor. So, remember this arrow is pointing outwards in NPN transistor and for PNP transistor the arrow is in the reverse direction. So, this is NPN transistor and this is PNP transistor. Now, for general purpose both function equally good, but NPN has a at one point it is superior to the PNP transistor. Let us consider silicon transistors for example. In NPN transistor, as we will go through the working of a transistor, we will see that electrons are the major players in the in transistor action. So, electrons are having higher mobility, they can these transistor NPN transistor will work up to a higher frequency as compared to PNP transistors. In PNP the major contributions will come from holes, while here they are from electrons, electrons being of higher mobility. So, NPN transistors can function up to higher frequency of operation. So, we will, because when we talk of the physics of the transistor, we can talk in terms of PNP or in terms of NPN, but and one and the same thing. Here in NPN when we talk the role of electron, that is to be replaced by the role of holes when we talk of a PNP transistor. So, remember that we will confine our discussion mostly to NPN transistors. And now let us see first some construction aspects. Let us talk of sizes first, sizes. The emitter it is of moderate size, that is emitter has dimensions between the dimensions of collector and base, and base this is thinnest, and collector as far as when we compare the three sizes in a transistor, size of emitter, base, collector, then collector has the largest size. And to give you the actual dimensions, when we talk of a NPN transistor, then in discrete devices this total length may be around a centimeter. This is, we are talking of discrete transistors, and in integrated circuits where this is all on a chip, the sizes are reduced dramatically and the size may be smaller than a millimeter. So, anyway, for us this is good enough that the size is around 1 centimeter. Now, base is thinnest, this is moderate and the collector is largest. Why these sizes are like that? That will become clear as we proceed to understand the working of the transistor. Now, let us talk about the doping levels in the 3 regions. Doping levels. Emitter is heaviest doped. Base least doped, and collector is moderately doped. So, remember, in all transistors electron will emitter will have heaviest doping and base the least doping, and collector has moderate doping. Again, this will become clear why we need thin base which is least doped, moderately sized and heaviest doping for emitter, and collector is largest in size, but is moderately doped. How actually transistors are manufactured? So, making of transistors. There are 2 processes which are widely used. The one is process of alloying, and the other is the diffusion process. The earlier transistors, I am talking of 50s and 60s, the process of alloying was very popular, but it has been taken over by diffusion process, which is of course very widely used and one of the mostly used process for making integrated circuits. In integrated circuits there are 2 or 3 different processes. One is diffusion process, the other is ion implantation and epitaxial growth of different layers. So, that is they are reserved for integrated circuit fabrication, but discrete devices can be fabricated by process of alloying and diffusion process. Let us first talk what is this process of alloying. We take a small crystal of say p type silicon, p silicon, and on one side we put a small dot of a pentavalent impurity. This is like phosphorus, pentavalent impurity. This is, and now let us take this in this position. Actually there is a large crystal and thickness is very little, almost a millimeter, but this size can be 2 inches, 4 inches, and these pellets in the form of small dots are put on one side of it, and then the whole arrangement is put in a furnace which is very well controlled in its profile and in its temperature. So, this phosphorus impurity will diffuse and will make here N type. So, this will make a N type region here. So, this will be emitter, actually this will behave finally emitter, and when we reverse this side, then we put bigger pellets of phosphorus, and again we heat treat it. Here this is the larger pellet and this is again phosphorus, we heat treat it. So, it will diffuse and another N type semiconductor will be developed. So, and this we cut actually ultrasonically. So, from a 2-inch dia wafer of silicon, after these 2 treatments of alloying process, we can get say 100 or few hundred transistors, very small transistors, and so we will make the ohmic contacts. This will be the base. So, this is finally what we have is this here, this is emitter, this is collector, and the original one, this was, we will put a contact here, this will act as base, this will be collector, and this will be emitter. And as I said that these dimensions will be almost of the order of centimeter when you see it from outside, but actual size of the crystal will be a fraction of a millimeter, just 1 millimeter in cross section and less than a millimeter in thickness, but then it is put in a plastic or metal casing. This is what we see transistor when we handle it discretely. And so, the size of that can in which they are contained is of the order of centimeter, while the actual element has dimensions of the order of this is hardly a 1 millimeter. So, this is process of alloying, these are encapsulated, and finally, what we get is the metal can with 3 leads, one is emitter, base and collector. The other process is diffusion. Diffusion. This is again the starting point is a wafer, a silicon wafer, which is having dia, they may vary from 2 inches, 3 inches, 4 inches and even 6 inches wafers are widely used, and that if we want to make NPN transistor, then this will be P type silicon. Then this is put in a furnace, temperature is raised to above 500 degrees, but much less than the melting point of silicon, and then this is exposed to pentavalent vapors. So, this may be for example phosphorus vapors. So, diffusion of this phosphorus will occur and this will make a N type silicon here. Then it is reversed and we can change, because if this is emitter, then here the doping density requirement is high. So, this will be having much higher density of phosphorus, and when we reverse it, then we can choose actually the concentration of the phosphorus in the vapor pressure, and there are several controlling parameters. So, when we reverse it, this already contains the N type semiconductor here, then we again exposed to a pentavalent impurity of different vapor pressure and partly the contents. So, a N type semiconductor will be created here. We started with a P type semiconductor. Both sides now have N type, but they differ in their doping levels, and ultrasonically we can cut, and each one will be a small chip like this, on which electrical contacts can be made, and then this can be a transistor. This will be base, collector and emitter. This is much more popular nowadays to make devices. So, this is the fabrication of transistor. Let me make few more points clear, that this transistor is bipolar junction transistor. Or in brief, very popularly it is called BJT. What is the meaning of bipolar here? Of course, this is a junction transistor. There are two junctions, one is emitter base junction, another is the collector base junction. But why it is called bipolar? This is called bipolar because for the working of this transistor, as we will see, electrons and holes both are required for its operation. So, because of the requirement of electrons and holes, this is called bipolar transistor. In contrast to this, field effect transistor, which is popularly called as FET, this is a unipolar transistor. For the operation of a FET, either electrons are required or holes are required, but not both simultaneously, and that is why it is called unipolar transistor. So, this is the brief introduction to this, to the transistors. Now, let us see what happens when a small region, what we call base, is having on both sides a N type regions. So, this is first is a unbiased transistor. Unbiased transistor, that means by unbiased we mean that there is no external voltage applied to the device yet. So, let us see what happens. So, here this is N emitter, this is P base, and this is N the collector. Here there are majority electrons, here also majority electrons, and in p type material this is base and there are holes. Very heavily doped, that means very high density of electrons here. This is very lightly doped. So, there are fewer holes here, and this is moderately doped n type collector. Now, we have discussed that when n and p semiconductors meet at a junction, and if there is a structural continuity, then the diffusion process, the diffusion of electrons and of course of holes will occur here, and a junction will be formed as we discussed in the case of the diode. So, a junction is formed here, and that junction is called emitter base junction. This is called emitter base junction, and popularly it is enough to write it as emitter junction. Similarly, the diffusion of electrons will start from collector to base, and fewer holes will diffuse from base to collector. And again, for the same reasons as we discussed earlier, a junction will be formed here. So, this is the what we call base collector junction. Base collector junction, or simply we may call it collector junction. Now, these junctions, emitter junction and collector junction, let me draw another diagram to illustrate that these are the space charge regions. So, the figure is this. These are the bound charges. What is this? Because from this region the mobile charges, electron and holes, have disappeared, leaving behind the exposed space charge. Earlier electrons and holes were here. You remember that pentavalent impurity phosphorus, this will have 5 electrons, 4 will make the covalent bonding with the silicon, and the 5th electron, which is loosely bound, it disappears. So, on this side it will be a positive ion, and here on the p side there will be a negative bound charge. So, this is the space charge region and high resistivity region. When we apply a field, a voltage between emitter and base, then that voltage will give rise to field across this junction. And similarly, here electrons and holes have disappeared from here, leaving behind a pentavalent, a singly ionized impurity atoms here. They are immobile, they take the lattice positions. So, they are rigid and they do not move, but they are ions, because they are ions. So, there is a charge associated with that. The negative ions on the p side, the positive ions on the n side, and this is the electrostatic charge which gives rise to contact potential, which will be in the two cases may not be exactly same, because the doping of this region and this region, they are different. So, we have a potential energy diagram for the transistor can be drawn, and this is like this. If we just see this was the potential energy diagram for this was p type. In the case of diode we discussed, this is n and this is also n, and here this is conduction band edge, this is valence band edge, and this is emitter, this is base, and this is collector, and here there are electrons, here also these electrons, and here these are holes. This is the electron energy which goes in this direction, electron energy, while hole energy goes in the opposite direction. This also we had discussed earlier. This is the hole energy. So, once the junction has been formed, these charges from n side, though they have higher population. So, there is a density gradient, but they will be unable to cross over to the base region or to the collector region because of this barrier height, the contact potential. Similarly, these holes cannot flow towards the emitter or towards the collector, because this is not the downhill, this is also the uphill for the hole. Holes here have higher energy than this, and they do not have this much energy. So, that they will also be unable to move either towards n or p. So, this is the picture of NPN transistor in equilibrium when there is no external field applied to it, and this is how the junction remains formed. Now, what will happen when we bias the transistor? So, transistor with applied external field that means transistor with biasing. In the case of a PN diode, there was only one junction and there were two possibilities to bias that. That junction could be either forward biased or reverse bias. Now, transistor has two junctions. One is the emitter base junction, which we are calling as emitter junction, and the other is base collector junction, and that we are calling as the collector junction. So, there are more than two possibilities. Three schemes of biasing prove very useful for the transistor. The one is when both the junctions are forward biased. The other scheme is when both the junctions are reversed bias. And the third scheme is the emitter junction is forward biased and the collector junction is reverse biased. These are the three schemes which we will be discussing. Now, when both the junctions are forward biased, this is also called forward bias. When both the junctions are reverse bias, this is also called reverse bias. And the third scheme, when emitter junction is forward biased and the collector junction is reverse biased, this is called forward reverse bias. So, these three schemes we are going to study. First, we take forward bias. And simple circuit we can draw. These are ohmic contacts. For the time being, let us forget about this part. So, we just consider the emitter and base junction which is forward bias. Now, before discussing this forward bias, let me talk that we are discussing basically the application of transistor in amplifier circuits. Now, what is amplification and what is required for getting amplification? Amplification is, for example, if we talk of voltage amplification, then the input signal, normally our signals are AC and we are interested in their amplification. So, at the output it should be amplified, that means magnitude of this should go up without changing the shape and without changing the frequency. This is the meaning of amplification. If we talk of voltage amplification, that is a voltage wave, and if we talk of current amplification, this is the current wave. Now, when this will be possible? When this will be possible? When the output current or output voltage varies in accordance with the input current and voltage. I repeat, the amplification is possible when output current or voltage varies in synchronization in accordance with the input voltage or input current. If the currents are not varying, if they are independent, we cannot expect amplification, or if they are not varying linearly, they have some other relationship, then the output wave shape will be different from the input wave shape. So, that will imply distortion, and distortion may be in terms of amplitude distortion, phase distortion, or frequency distortion. We want true representation of the input signal in the output. So, only the magnitude of that quantity of interest should be higher, nothing else. In this case of forward bias, for the time being we forget about this circuit, collector circuit, and we talk about the emitter. A emitter junction is forward bias. This N type semiconductor is connected to the negative of the battery. What will happen? That this will reduce the barrier height we have discussed. Now, here we can bring out our knowledge of PN junction, that when a PN junction is forward biased, then a heavy current flows which varies exponentially with the applied voltage, and that will be consisting, the current will be arising because of the electron diffusion towards the base, and because they are in a heavy density of electrons is here. So, this component will be much higher, and to that will be added a small component which will arise because of the diffusion of holes. So, this will constitute heavy current. So, we will observe a heavy current I E. Similarly, so we talk of the collector junction, collector base junction, which is also forward bias. This N type collector is connected to the negative of the battery. So, this junction is also forward biased. Here also heavy current will flow, when the influence of this is secondary, is very little, and that we will see later when we talk of current voltage characteristics of the transistor. So, heavy current will flow. So, this will be a heavy IC. So, what we get in this forward bias? High emitter current and high collector current. The two currents will be very high, but one thing which is very significant and that is important when we talk of amplification. If we make this current 0, for example, this is unbiased at the moment, then this current still remains the same, almost the same. So, I E will not depend on I C. Similarly, if we consider the collector junction, the current IC will continue to flow as long as this junction is forward biased, and if we disconnect this or if we vary this voltage, will it affect collector current in this situation? No, because they are almost behaving independently. So, collector current, the output current will not depend on the input. This is in violation of what we discussed about amplification. How amplification will occur? We are creating a signal here, and this should be amplified, which is possible only when the output voltage or current varies in accordance with the input signal. So, that will not happen. So, in spite of the fact that high emitter current and high collector current flows in this circuit of emitter junction forward biased, collector junction forward biased, but the two currents are almost, this is important, almost independent. So, IC does not depend, is not the function of the input current IE. This is very important for this case. Since the collector current is not the function of the input current, this arrangement cannot work as a amplifier, cannot work but we will see that in switching states this situation will be representing one of these states of the switch. So, as far as amplifier applications in amplifying are concerned, then this biasing scheme does not work. Next, we consider the reverse bias. Reverse bias. Here in fact, this point in forward bias we could have discussed by the potential energy diagram also. So, let us first take that, then I will take reverse bias. This was a unbiased potential energy diagram. Now, we have applied forward bias on both sides. So, forward bias creates the field opposite to the built-in field. This point we discussed in the case of the junction diode, and the potential height will fall. These red ones are the new positions. This is the reduced potential here, this is reduced, and hence these electrons from the n side will constitute what we call emitter current, and similarly the electrons, and of course a small number of holes will also diffuse towards the emitter. So, that will be the part of the emitter current. They will also diffuse towards the collector, but the major contribution of collector current will be from the electrons. So, that will constitute the whole current. But the fact that the two currents are independent, that makes the use of this biasing scheme not suitable when we are going to use transistor as an amplifier. Then we take reverse bias. Here the emitter junction is reverse bias, the collector junction is reverse bias, and we understand from our knowledge of p-n junction, when it is reverse bias, then very feeble currents, at least 3 or 4 orders of magnitude is smaller than the currents which we observe when the junction is forward bias. So, such minute currents arising because of the thermally generated charge carriers in the junction and near the junction, they constitute what is known as reverse saturation current. So, what we will get here is small emitter current, very small emitter current, and which will be because of the thermally generated charge carriers, minority carriers, that means holes in the n side and electrons which are in minority on the p side, they both will drift with the applied field. This is positive. So, the electrons will be dragged towards this electrode and electrons will be dragged to this, and they will constitute the current. So, very small emitter current. Similarly, let us see what happens at the collector junction. At the collector junction, again this is the reverse bias junction. So, there will be very small collector current. Very small collector current, which will of course be arising because of the minority holes drifting from the collector towards the base and minority electrons drifting from the base towards the collector. So, that will constitute the collector current. Here also the situation is that collector current I c will not be dependent on the input current. The two currents are independent. If we switch off this current, still this current will continue to flow, and similarly if we switch off this, then this current, but the significant point is that I c, the collector current does not depend on input current, the emitter current. So, therefore, this can also not be used as for amplifying purposes. We will continue this discussion. We can discuss this point, this reverse bias from a potential energy diagram point of view, that we will be discussing, and then we will go further.